Welcome to the Easy Math Guide. Now guys, I got a great comment asking for a general overview of mean moment estimators and asymptotic distributions. These are kind of tricky statistics concepts, so I'm gonna try and break them down where they're fairly easy to understand, alright? So we're gonna start with these mean mode estimators, or MMEs, okay? And this is just for you to estimate population parameters with sample moments and the method of moments. So the method of moments is where you match sample moments to the population moments. So for example, our first moment would be the mean, the second would be variance. This is just a way of estimating these unknowns when you're dealing with probability distribution. Okay, so there are some key steps. First, you want to find your population moments. So these are your mathematical expectations of powers of random variables, and I labeled them right here. And then second, you're going to set these sample moments equal to the population moments, kind of how I did right here. And then you just solve. So this example down here, we're going to pretend that we have a population where random variable x follows a uniform distribution, and then we're going to try and estimate the unknown parameter of theta using the method of moments, all right? So step one is just to find your population moment. So we've got our mean right here, and we're setting it equal to theta over 2, okay? And then you set the sample moment equal to the population moment. So we have our sample mean, setting it equal to theta over 2, and then the math is fairly easy from here. Now we just want to know what the heck theta is. So if our sample mean is equal to theta over 2, well, the opposite of dividing by 2 is multiplying. So if we were to multiply both sides by 2, we would get theta all by itself. And that's just equal to 2 times our sample mean. And then you're always going to be given some sample data. So I put a little list up here. And your last step is just to use that sample data to figure out what the heck theta is. Okay, so you're going to take your mean. So we're going to add up these 5 numbers. We're going to divide by 5 because, there's 5 of them. So 20 divided by 5 gives us 4. Well, then we're going to plug that back in for our sample mean. And then 2 times that sample mean is just 8. So that would be our final answer. I'll just give a final big kind of overview of this mean mode estimator right here. And now we're jumping into asymptotic distribution. Okay, so as the video plays, you're going to see I kind of outline some important keywords here and there. But basically, what asymptotic distribution is, it tells us all about what happens when you have big sample sizes. So as your number of samples gets bigger, your estimator, such as a sample mean, it's going to start to be really predictable. It's going to start to follow that normal limit thanks to the central limit theorem. And as your number of samples increase, these estimators are going to become more accurate and they're going to approach their true value. There's also going to be a lot less variability and we're going to hit that normal distribution, whether the data does or not. Okay, so now we're going to do a little example down here. So pretend we're studying the heights of kids in school. So we're just picking a bunch of random kids, we're taking their heights. So we know this mean is 65, we know the standard deviation is 5. So we're going to take bigger samples just to see what happens to this mean. Now for the sake of this example, I'm not going to list out all of the heights, especially when we get to our large sample. 500's too much. Okay, so this first one. Pretend when we measured these 5 kids' heights, it added up to 328. So when you do that division, you get 65.8. Okay. When we add up these 30 kids' heights, pretend it added up to 1,944. Divide by the 30 kids, you get 64.8, which is a little closer to our mean. And then next, we are going to do our large sample. Okay, so when we add up these 500 kids' heights, pretend that it came out to 32,510. And then divide by that 5,000, and then you get that 65.02. Okay, and that's way closer to our 65 mean, almost perfect. Okay, so our conclusion, as you increase your sample size, your sample mean gets really, really, really close to that true mean. So according to the central limit theorem, as n approaches infinity, or just our sample getting much bigger, that sample distribution is pretty much normal, and it's going to be very, very true to the actual mean. Okay, so I hope this was a pretty good overview of these 2 statistics comments. If any of y'all have further questions, please reach out. And feel free to drop a comment below if there's any other math help that you guys need, regardless of the subject. Thank you for watching.